Hi everybody, Dr. A here, and in this video we are going to be exploring an example of a two-dimensional rigid body. In this video we're being asked to draw the free body diagram of the system and apply equilibrium equations to solve for the external support reactions. So let's take a look at what we have in this figure. If you notice at point A over here we have a nice little triangular symbol. That is the symbol for an external hinge or pin connection. On the opposite side, point B, we have a little circle. That's our roller connection. So this is what we call a simply supported beam. Within the first 6 feet of this beam, we have a uniform distributed load of 0.2 KLF. And if you remember, KLF stands for kips per linear foot. 2 feet to the right of the ending of that uniform load, we have a 0.75 kip point load that is at a 60-degree angle from a horizontal reference axis, okay? So as we get started tackling this problem, you need to write everything down. Remember, math and engineering is not a spectator sport. You got to participate by writing down neat and organized notes. So let's go ahead and get started. We're going to get started by writing the word solution. And we'll get our solution started by drawing a free body diagram of the entire system. So if you remember, what is a free body diagram? Well, it is a simple figure, a simple drawing of your system that shows all of the known and unknown forces, reactions, and dimension lines. So at point A, what do we have at point A? We have an external support reaction that's a pin. So a pin has two forces that generate a reaction. We have a vertical force reaction that we can call AY, and we have a horizontal force reaction that we can call AX. And then at the opposite side, we have this roller. Well, what happens at a roller? You have a normal force reaction that is perpendicular to the surface on which the roller is resting. So if you notice, this roller is resting on a horizontal surface, which means that the force that will develop is going to be perpendicular or normal to that horizontal surface. That means that BY is pointing in the vertical direction. Now, before I draw anything else on here, I want to ask you a question, and I want you to pause the video and think about it, and then I'll tell you the answer. You can unpause and I'll tell you the answer. So my question to you is, do you know what direction these unknown reactions are pointing? For example, do I know for sure that AX is pointing to the right? Do I know for sure that AY and BY are pointing up? Pause the video and think about it. Okay, so I'm going to tell you the answer now. The answer is not really. We don't really know if AX is pointing to the right. It could be pointing to the left. And the same is true for AY and BY. We don't know for sure that they are pointing upwards. We do know they're vertical, but we don't know if they're pointing upwards or downwards. They could very well be pointing down. So if you remember from maybe your previous knowledge in statics, what we're doing here is we are assuming the particular direction that these three unknown forces are pointing. So we know AX is horizontal, but we are assuming it's pointing to the right. We know AY and BY are vertical, but we are assuming they're pointing upwards. Now, when we do our calculations in a minute with our equilibrium equations, if our values that we calculate come out positive, it turns out that the direction we have assumed in this free body diagram is the correct direction, and they are in fact pointing in the direction that I drew here. If our calculated values for AX, AY, or BY become a negative number, it actually turns out that those reaction forces are pointing in the opposite direction of what we assumed in this free body diagram. So put that idea in your back pocket now, and we're gonna revisit that here in a minute after we do some calculations. So let's continue to draw on our free body diagram. We also have to draw all of our known forces and other information on here. So we know that we have a 0.2 KLF uniform distributed load here. We know that we have a 0.75 kips point load here at a 60-degree angle. And we know these dimension lines. Remember, drawing the dimension lines is part of the free body diagram that should always be included on there. So here's our completed free body diagram. So that's part of the solution. The next part of the problem said apply equilibrium equations to solve for the external support reaction. So let's do that. What we're going to do is we're going to look at this free body diagram. Just look at what we drew. And we remember from statics that for two-dimensional rigid bodies, we have three available equilibrium equations. Sum of the forces in the x direction equals 0. That's one of them. The other is sum of the forces in the y direction equals 0. And the third equilibrium equation for two-dimensional rigid bodies is sum of the moments about a particular point equals 0. So let's go through these equilibrium equations systematically and use them on this free body diagram to solve for our three unknown force reactions, AX, AY, and BY. Let's start with sum of the forces in the x direction equals 0. So when we write this equilibrium equation, we have to put up above the sigma symbol that things pointing to the right are what we are going to take as positive. So this little symbology right here shows that anything that has a force component pointing to the right, we're going to call that a positive number. So now let's look at our free body diagram and let's move left to right and see what all has an x component. Well, the first thing we encounter, of course, is AX. We see that very clearly right here. AX has an x component, which is itself, okay? The next thing we encounter is AY, but you notice AY is pointing straight up, so it does not have an x component. The next thing we encounter is the 0.2 kips per foot. Well, that distributed load is pointing downwards. Again, no x component there. But what about this 0.75 kips? Notice it's at an angle, and because it's at an angle, it has an x component, and specifically, it has an x component that is pointing to the left. So I can really small here point a little x component pointing to the left there that represents the x component of that 0.75 kips. So we're going to include that into our equilibrium equation by saying minus 0.75 kips times the cosine of 60 degrees equals 0, okay? And again, that cosine of 60 degrees is what is going to get us the x component of this 0.75 kip vector. And then, of course, by is vertical, so it does not have an x component. That's why there's no sign of by in this equation. So we do some rearranging, and we can solve for ax. And when we solve for it, we get 0.375 kips. Now, when we calculate that as 0.375 kips, it came out positive. That's a positive 0.375 kips, which means that it is actually pointing in the direction we assumed for AX, which is to the right. And so off to the side, I'm going to put a little vector symbol pointing to the right there. So that's one of the unknowns that we needed to solve for. Now we need to solve for AY and BY somehow. So we're going to use our other two equilibrium equations. The next equilibrium equation I'm going to use is sum of the moments equals 0. Now, if you remember, the sign convention for summing moments that is typically used is rotations going counterclockwise are taken as positive. And you also should remember that when you sum moments about a particular point. It doesn't really matter what that point is. It just needs to be a convenient point on the system that can make your life a little easier when it comes to calculations. So I'm going to say sum of the moments about A equals 0, but know that you could also sum moments about B and it would be about the same amount of work. But I'm going to sum moments about A. So summing moments about A, I'm going to move left to right. First, AX and AY are not going to be in this equation. The reason is because they're acting at point A. So there is no perpendicular distance between those forces and the point A that we are taking the moments about. So because there's no perpendicular distance, that means AX and AY, neither of those two are causing a rotation around or about point A. The first thing that's going to cause a tendency of rotation about point A is the 0.2 KLF, okay? So if you notice, 0.2 KLF it's pointing downwards, which means if you look at this, it's going to cause a clockwise tendency of rotation about point A. All right, it's going to try to spin around point A in a clockwise fashion. So we're going to say minus 0.2 kips per foot times 6 feet times 6 feet over 2. Now, where did that come from? Well, the 0.2 kips per foot times the first 6 feet, if you remember from statics, it gives us our equivalent point load right here. Now, that equivalent point load is located at the centroid of that distributed load. And the centroid of a uniform distributed load is right smack dab in the middle of it, which is at 6 feet over 2 distance away from point A. So that means our moment arm, or our perpendicular distance as we call it sometimes, about point A is going to be the 6 over 2. All right. Next, we see the 0.75 kips. So the 0.75 kips is going to cause a clockwise rotation about point A, but we need its vertical component, right? So we're going to say 0.75 kips times the sine of 60 degrees, and then times its perpendicular distance, which is 8 feet. So let's talk about why that is very quickly. So we're going to look at the vertical component here, because the vertical component of that 0.75 kips is what is generating the tendency of rotation about point A. And so the vertical component is 0.75 kips times the sine of that reference angle, which is 60 degrees. And then its perpendicular distance away from point A is this 8 feet right here, okay? And then last we see BY. BY is going to cause a tendency of rotation about point A, and that's going to be counterclockwise, which we call counterclockwise rotations positive. So we're going to say that's plus BY times its perpendicular distance away from point A, which is 10 feet, and then all of that equals 0. So solving for BY here, you should end up getting a positive 0.88 kips. And if it's positive, that means that BY is pointing in the direction that we assumed it to be in our free body diagram, which is in fact upwards, okay? So please pause the video, punch this through in your calculators. Don't just trust me. Check these numbers yourself and make sure you know where these are coming from. Our last equilibrium equation we're going to use is sum of the forces in the y direction equals 0, and we're going to take vector forces pointing up as positive. So looking back at our free body diagram, you want to look at everything that has a vertical force component in this entire free body diagram. The first thing we're going to encounter is AY. AY is pointing upwards. So we're going to start with just writing a positive AY. The next thing we encounter is that distributed load, the 0.2 KLF. Now, we need to find its equivalent single force, because right now the 0.2 KLF is not a force, it's a distributed force. It's kips per foot. You need it just to be kips. So we're going to say minus 0.2 kips per foot times the length over which it's distributed, which is 6 feet. The next thing we encounter is the 0.75 kips, which is pointing down, but you're looking at y components. We're looking at vertical components, so we need its vertical component specifically. So we're going to say minus 0.75 kips times the sine of 60 degrees. And then the last piece in our free body diagram that we encounter is BY pointing up. Now, we already solved for BY in our previous step. Here it is in our previous equilibrium equation. So we're going to say plus 0.88 kips equals 0. And we're going to do some rearranging here. And we're going to end up getting AY is 0.97 kips reacting upward. So in summary, our external support reactions are AX is 0.375 kips reacting to the right, AY is 0.97 kips reacting upwards, and BY is 0.88 kips reacting upwards. And that's going to conclude this example. Thanks for watching. Please hit like and subscribe.